In the name of Almighty God, I am Mahsa Sankoshi, and today I want to talk about astrophysical reaction rates for charged particle-induced reactions on proton-rich nuclei. It was written by Thomas Raucher from the Department of Physics, University of Basel, Klingel Begresti, Switzerland, and also the Hertfordshire in United Kingdom. Astrophysical reaction rates for reactions with proton-rich isotopes of Ne to Bi from stability to the proton tripling were calculated with an updated version of the SMART statistical model Hauser Fechbach code. Here the focus was on reactions with protons or alpha particles as required for nuclear synthesis in proton-rich matter. For completeness, also neutron-induced reactions are provided for the same set of targets. Some comments on dependencies of rates on various nuclear properties and on the appropriate way to compare the two experiments are given. The news rate set for charged particle-induced reactions provides a better description of experimental data than previously widely used rates, especially for reactions involved alpha particles. The keyword for this article is astrophysical reaction rates, Hauser-Fechbach model, and nuclear synthesis. The introduction section. Nuclear reaction rates provide the basis for all astrophysical investigations concerning energy generation and nuclear synthesis in the early universe, as well as in hydrostatic and explosive nuclear burning of stars and stellar objects. They are driven from experimentally measured and or theoretically predicted nuclear reaction cross sections. A direct experimental determination of reaction cross-sections at the interaction energies relevant to astrophysical environments is possible only if the involved nuclei are accessible for reaction studies, for example, are stable or have sufficiently long half-lives. Cross-sections are sufficiently large and thermally excited states of the target nuclei don't contribute considerably to the reaction rate in an astrophysical plasma. Therefore, the majority of astrophysical reaction rates used in astrophysical simulations are based on the theory and they may rely on indirectly on experimentally obtained information required to inform the or theoretical treatment of the nuclear properties using the reaction models depending on the relative energy and the level density of the interacting nuclei. Different reactions models are employed for target nuclides of intermediates and high mass number. When it is much more larger than 20, the relevant excitation energy of the compound system formed from the combination of the projectile and target in most cases is high enough to apply the statistical model of nuclear reactions originally proposed by Bohr and later refined by the reference 2 and 3 at low level density at the compound formation energy or at high interaction energy. Individual resonances and direct reaction mechanisms have to be considered respectively. For example, in reference 4 and 5 for an overview, the statistical model approach following, also called Hauser-Fachbach model, has been applied in the calculation of the thermonuclear reaction rates for the astrophysical purposes by many researchers, with early investigations only making use of ground state properties of nuclei. Soon after, the importance of an inclusion of excited nuclear states was pointed out. Extended compilation have been provided by the reference 8 and 9. More recently, further compilations have been published based on the codes Smoker in reference 10 and non-smoker in reference 11 and 12 and Thales in reference 13. Most recently, the code SMART Guard has been developed as a successor to a non-smoker with improvements in the treatment of charged particle and photon transmissions in the nuclear level density, and with inclusion of recent experimental information on low-lying excited states. Reaction rate compilations obtained from calculations using non-smoker antilles are presently the ones utilized in large-scale applications in all subfields of nuclear astrophysics. When experimental information is unavailable, a small guard has been used to analyze experimental data and for improvements for constrained sets of the reaction rates, but a large-scale set of reaction rates has not been published yet. In this work, astrophysical reaction rates from small god for charged particle induced reactions are presented, superseding and extending the preliminary evaluation given in reference 14. Differences to previous calculation are summarized, and general remarks on the dependence of rates on various nuclear properties also important in the comparison of experimental and theoretical rates are provided. The next section can be definition of astrophysical reaction rates. Astrophysical reaction rates count the number of reactions of a specific combination of projectile and target nucleus occurring per volume and time in a plasma with given temperature T. The energy distribution of atomic nuclei in astrophysical plasmas is given by the Maxwell-Boltzmann distribution. To obtain a rate, the energy and temperature dependent reaction stellar cross sections sigma star have to be weighted by this energy distribution multiplying this reactivity. For example, rate per particle pair with their respective number densities Na and Na capital of the interacting nuclides. The two body reaction rate, you can see that Ra plus capital R is equal to Na multiplied by n capital R divided by 1 plus delta I R multiplied by sigma star nu is equal to n R n capital R divided by 1 plus delta R capital R multiplied by square root h divided by p micro multiplied by 1 divided by carve t to the power of 3 divided by 2, and the lower boundary is 0. The value for upper boundary is infinite. Sigma star Et, which is the temperature E, and small e is to the power of minus E divided by chi b to the power of T. Derivative of E is obtained in reference 5, which delta being the Kronecker delta to avoid doubling, containing micro being the reduced mass of projectile and target nuclide, and Kb is a Boltzmann constant or reactivity rate per particle pair is defined using angle brackets signifying the averaging or the energy or velocity distribution of the interacting nuclides. For particle application, there is a limited energy range across which the integration has to be performed because no significant contributions to the integral values come from outside this range. For the refer to the reference 15. This is called the gamma window. The quantity sigma star E and T is a stellar reaction cross section references 4, 5, 8, 16, including reactions not only on the ground states of the interacting nuclei, but also on their excited states, which are populated by thermal excitation in the plasma. Sigma star AT is equal to 4 divided by G0T sigma I, sigma J, 2J I plus 1 divided by 2J0 plus R1, EI divided by E, sigma Ij multiplied by EI. Summing over reactions leading from target levels I to final levels J, which cross sections sigma I and J, which EI is equal to E minus EI to the power of X being the center of mass energy relative to excited level I. The ground state is given by the I is equal to 0 following the reference 16, which is the value of sigma to the power of ij is equal to 0 for ai is less than or equal to 0. The spines of the target levels are populated by the thermal excitation are denoted by Ji and J0T is the part function of the target nuclide normalized to the ground states. J0T is equal to 1 divided by 2J0 plus 1 multiplied by sigma lower boundary is I 2GI plus 1 e to the power of minus EI to the power of x divided by KBT, with EI to the power of x being the excitation energy of the level I in the stellar cross-section. The contribution of excited states are weighted by the 2Ji plus 1 multiplied by E minus EI to the power of x divided by E is equal to 2Ji plus 1 multiplied by 1 minus EI to the power of x divided by E. This looks differently compared to the usual Boltzmann population factors exhibiting in an exponential suppression depending on the excitation energy to Ji plus 1 exponential minus EI to the power of x divided by KBT. The stellar cross-section in this form is obtained when transforming the Boltzmann-weighted sum of reaction rate integrals for each excited stage to the single integral shown in equation 1. This not only involves an exchange of summation and integration, but also requires a substitution of the integration variables, leading to the transform weights 4, 5, 8, 16. The use of stellar cross-section not only simplify the expression for the relativity, but also allows to judge the importance of excited states contribution better than by just examining Boltzmann population factors multiplied by integrals. The single integration of a stellar cross-section field provides better numerical accuracy in the calculation of a rate, and that is why it has been used in theoretical approach since reference 16. For example, you can also see reference 4, 8 until 11 and 13. Note that the temperature dependence of the stellar cross-section solely stems from the temperature dependence of the partition function, reflecting the increasing population of levels at a higher excitation energy with increasing temperature. Also note that equation 2 assumes that the projectile is in its ground state with its spin degeneracy included in sigma ij reactions considered. Here are two body reactions with light projectiles, specifically protons and alpha particles, for which this assumption is justified. Depending on the nucleus and the temperature, the summation equation 3 has to be extended into a region of excitation energy with insufficient knowledge of discrete excited states. In this case, above the excitation energy in last power of x of a last discrete level included an integration over the density rho of nuclear levels with spin J and power parity 2 has to be invoked. J0T is equal to 1 divided by 2J0 plus 1. The brackets show the accurate sigma. The lower boundary is I is equal to 0. The upper boundary is I less. And the element is 2Gi plus 1 multiplied by e to the power of minus chi I to the power of x divided by chi bt accurate is finished. So the rest of the formula for equation 4 is plus the integral lower boundary is e last to the power of x and the upper boundary is infinite, and the sigma is j 2j plus 1 e to the power of minus e prime divided by chi b rho e prime j to derivative of e prime. In practice, there is a finite energy for the upper limit of the integration. Section 3, the statistical model Hausser-Fachbach. To assure the applicability of the statistical model of nuclear reactions, the nuclear level density at the compound nucleus formation energy has to be high enough to assume overlapping resonance that permits the use of average resonance weight, as can be seen from the sum appearing in equation 5 below. An additional assumption is that in principal states, with all spins and parities are present and the compound formation energy, the statistical model cross-section is smoothed without exhibiting resonance features due to the fact that the calculation of the reaction rate involves an integration over an energy range, for example, an energy average of cross sections. See equation 1. The criterion for the applicability of the statistical model is more relaxed when applied to stellar rates than to reaction cross section. A smaller number of contributing resonances can be sufficient when applying the energy average of a statistical model cross section, because resonance features in the actual cross section are smoothed out anyway based on the reference 17. For the majority of reactions of astrophysical interest across the nuclear chart, it has been shown that a statistical model is applicable to the calculation of astrophysical reaction rate based on the reference 17. Exceptions are target nuclides with low mass number at shell closures for rates at low temperature, and towards the drip lines. The statistical model cross section for a reaction R plus R to the power of I, which includes CSC plus, which includes BJ plus B, including transitions from the I level in target nuclide or to the J level in the final nucleus B, where compound state C in nucleus C reads that the sigma HF to the power of IJE is equal to P divided by chi I to the power of 2 multiplied by 1 plus delta R, a capital R and a small r divided by 2Ji plus 1 multiplied by 2 Ji plus 1 multiplied by sigma m. The lower boundary is J, 2 J average, L, J prime average, L prime into J plus 1, tau J 2 L, J average, to the power of I, EI, tau J 2 L prime, J average prime, to the power of J divided by sigma. Lower boundary is C, L, J average, tau unique vector, C, J LJEI multiplied by WAI with the transmission coefficients tau for particle or photon transitions at the compound formation energy. EI is equal to E plus SL connecting to a compound level with spin J and parity 2 with initial states I and final state J respectively with separation energy of the projectile in the compound nucleus is denoted by SR. All quantum mechanically allowed channels, spins, J period, and partial waves L are included in the summation. The denominator contains a sum over total transmission coefficients test to the power of C, including all energetically possible transitions from the compound stage to any final stage. This includes the ones in the nuclides, any A and B, but also in all other nuclides reached by photon and particle emission. The energy dependent factor W is the Watt fluctuation correction and includes non-statistical correlations between initial and final states. It is of the order of W is equal to 1 for most energies expects close to the openings of additional reaction channels. There is a simple relation between average resonance, white tau average, and transmission coefficients tau j 2 l j average EI is equal to 2p rho EI j 2 tau average j 2 l j average EI with the nuclear level density rho taken at the compound formation energy EI As for the partition function, equation 3, also in transmission coefficient sums over discrete levels have to be replaced by integrations over a level density above the last now discrete level. Therefore, the level density enters in two ways. First, the level density in the compound nucleus at the compound formation energy determines whether the statistical model actually is applicable. Second, the level densities in the various nuclides reachable from the compound levels determine the part the transmission coefficients. The impact in the latter case depends on the particle separation energies at the difference between compound formation energy and particle separation energies determines whether the region of low-lying discrete states has to be supplemented with a region covered by using the level density. With a small energy difference, transitions to discrete states dominate transmission coefficients, and the impact of a level density will be small. For a study on the sensitivity of the astrophysical reaction related to variation of the level density, see reference 19. Now, I want to go to the fourth section, which is implementation in a SMART. Codes for calculating statistical model cross-sections mainly differ in the treatment of the nuclear properties entering the calculation of transmission coefficients as well as in the masses and excited states property used. Particle transmission coefficients require the use of optical potential describing the effective interaction between the particle absorbed and emitted by a nucleus. Electromagnetic de-excitations of the compound nucleus through emission of gamma radiation is described by phototransmission coefficients. These require knowledge of the photon strange function, specifying the range of an electromagnetic transitions emitting a photon with given energy. For details on the calculation of the transmission coefficients for the two cases, see, for example, the reference 4, 5, 8, 11. Here, results obtained with version v0.420s of the code SMART are presented. The code SMART statistical model for astrophysical reactions and global direction reactions is written completely in Fortran 90 and 95 with exception of the routines handling a web interface which are written in C language and has a modular structure making things easy. The latest nuclear data can also safely be included through files or web downloads. Code versions Blue V100S don't yet use the global approach for including direct capture. This will be presented in future versions. Direct capture is important close to the reply where the particle separation energy SR is low and where also few wireless space resonances or no resonances are present due to the higher relevant energy range for astrophysical reaction rates with charged particles than for neutrons, translating to higher excitation energy of the compound nucleus. Direct capture generally is more important for neutron captures than for charged particle captures in astrophysics. In addition to an updated implementation of nuclear properties listed below, some numerical improvements have been implemented in SMARAG. Of particular importance is the implementation of an improved method to calculate charged particle transmission coefficients, improving the method previously used in reference 20 in the non-smoker code by implementing a Fox Goodwin algorithm. You see, for example, 5 and 21 to solve the Schrodinger equation combined with a reliable routine to compute Colombo wave functions that is stable also far below the Colombo barrier. This affects transmission coefficients for charged particle reactions below the Colombo barrier and therefore most of these reactions in astrophysical environments masses were taken from the 2020 atomic masses evaluations OME 2020, based on the reference 2223, experimentally unknown masses and microscopic corrections for the calculation of the nuclear level density were taken from experimentally known spines and parities of ground states and lying states were taken from the 2021 ENSDF plus new base snapshots are provided by Ripple tree based on the reference 37 up to 40 levels were included, but only up to the last level for which an unambiguous assignment of spine and parity is present and up to which the level scheme can be considered as being complete. Above the last included discrete level with the energy E last to power of X theoretical nuclear level density description was employed. The description is based on the approach described in 1117, combining a constant temperature formula for low excitation energies with a backshifted Fermi gas formula having a level density parameter that depends on the excitation energy based on the reference 17. In this previous description, the parities were assumed to be equidistributed. Here, a parity distribution also depending on the excitation energy is implemented in reference 26. The calculation of particle transmission coefficients require the use of the optical model potentials to describe the effective interaction between the projectile and target nucleus. For neutrons, the microscopic potential of Legion in 1980, based on the reference 27, was used. This is based on the microscopic potential of based on the reference 28, but specifically adapted for low energy scattering as encountered in astrophysical applications. This approach was used for neutrons and protons, also in the smoker and non-smoker codes. In the smart card, a modified version of the Legion in 1980 potentially is used for protons. Comparisons to experimental data motivated in an increase of the depth of the imaginary part. This may also be adequate for the neutron potential, but since no comparison to neutron data has been made so far, it was decided to use Legion 1980 potential for neutrons as previously defining an optical potential for alpha particles that is at the same time applicable to a large range of nuclides and also at the low subcoulomb energies encountered in astrophysics has been a long-standing problem. Many suggestions for such general low energy alpha plus nucleus potentials can be found in literature. See, for example, 32 for an overview. The smoker and non-smoker Coates had used the global potential by 33 despite its overall success over the past decades. It became apparent that improvements are required for low energies. Most recently, the atomic V2 potentials have has shown promise in reproducing modern experimental data at low energies based on the reference 34 and 35 and is also implemented in SMART. The real part of the atomic V2 potential is falling potential and requires the acknowledge of the nuclear matter density distribution in nuclides. Therefore, the folding potentials of 35 reference were available and theoretical nuclear density distributions 36 were used to compute the required folding potentials. Otherwise, in the calculation of the transmission coefficients for electromagnetic transitions, a gamma exchange function is folded with the number of available levels, discrete levels or integrated level of a nuclear level density for given gamma energies included by E1, M1, and E2 transitions. The strange function for dominant E1 transitions, giant dipole resonance GDR was computed using a Lorentzian shape but with a modification of the white at low energy. For deformed nucleus with deformation taken from 24, the GDR or giant dipole resonance is split into two contributions in the well-established manner. See also the reference 11. Experimentally known that a giant dipole resonance energies E GDR and white tau GDR were taken from the Ripple tree based on the reference 37. Beyond the experimental knowledge, the descriptions of the 38 was used. A straightforward application of the Lorentzian shape would overestimate the gamma range at low energy gamma. Therefore, an energy-dependent GDR or giant dipole resonance with Caprini GDR was applied following Caprini GDR E gamma is equal to T GDR square root gamma E gamma divided by E GDR for the M1 component of the gamma transitions. A simple single particle approach was used, leading to a dependence on the Q of a gamma energy based on the reference 8, the giant quadro pole resonance or GQR for obtaining Fe2 transitions was treated as given in 14 white and pink cross sections and 41 reference as energy. Now I want to go through the results for charged particle induced reactions. The dataset obtained with the code Smaragd are available online. See the section 8. They include machine-readable tables of reaction cross-sections, astrophysical reaction reactivities, and fit parameters of reactivities for target nuclides from Na to Be for isotopes from stability to the proton tripling. The full extension of the calculation can be seen in the figure 5 left, where the considered target nuclides are marked by open green squares for unstable target and open black squares for stable ones. Astrophysical reaction reactivities, including the effects of thermal excitation of the interacting nuclides, are provided for temperatures from the zero point 0.1 to 10 gigakelvin. Reaction cross sections for target nuclides in the ground states GS are provided for center of mass energies up to 14 mega electron volt, as this covers the range of the astrophysical important energies. Fits of astrophysical reaction reactivities are given in the standard react, reactor laboratory parametry station using 7 Fitch parameters all 0 until the all 6 with the reactivity to the computed from the this equation NAR sigma star nu R, which is given plus R capital R, which is given the B plus capital B is equal to exponential I0 plus I1 divided by T9 plus I2 divided by T9 to the power of 1 divided by 3 plus I3 T9 to the power of 1 divided by 3 plus I4 T9 plus I5 T9 to the power of 5 divided by 3 plus I6 logarithm T9, with NR being the Avogadro constant. This yields NR sigma star nu in cubic centimeter per mole second when the temperature T9 is given in a gigakelvin. Fit coefficients for the reactivity of the reverse reaction are also given. Note that for the reverse reactivity, the value obtained by the reaction laboratory parameterization has to be multiplied by the ratio of the partial function g0 to the power of r divided by g0 to the power of b, finally to obtain the actual rate. Both for the forward and reverse reaction, the values for sigma star nu have to be multiplied by capital R divided by 1 plus delta R and capital R, or N capital B divided by 1 plus delta B capital B respectively. All to emphasize, here is an charged particle induced reactions. The online table also include neutron induced reactions on nuclides in the same element and isotope rate as for the charged particle induced reactions. This is to provide a complete data set as astrophysical applications. More reaction rates should always be fitted in the direction of positive Q value except for captures, and therefore it is necessary to provide values For the case where the Pn and alpha n reactions have negative reactions key value. Now I want to go through the comparison to data. Some comments on comparing data to predictions. The use of the experimental data is always preferable to using theoretical predictions, and reaction rate set for implementation in nuclear network calculation usually includes a mix of experimental and theoretical reaction rates. However, it is important to realize that only a small subset of required rates, especially for nuclides in the intermediate and heavy mass range, may be fully constrained by the data. On the hand, reaction cross sections below the Columbus barrier become tiny and are difficult or currently impossible to measure, even for the stable targets. On the other hand, a measurable of gases cross sections as usual performed in laboratory experiments may only constrain a small contributions to the astrophysical reaction rate because the contributions of reactions on excited states of the target nuclides often dominates the rate, especially at the elevated temperatures encountered in explosive nucleosynthesis. For 1943-44, in such cases, the results of the measurement have to be supplemented or replaced by theory, with the data providing the means for assessing the validity of the theoretical treatment only of the gases contribution. The online table also includes the gases contribution to the total astrophysical rate as guidance, since the calculation of the astrophysical reaction rate involves integration or energy range, the relevant relative interaction energies for the reactions on the GS and the excited states. The sensitivity of the rate to change a nuclear property may be different from the sensitivity of the laboratory cross sections to guide experimentalities. Tables of the sensitivities of cross sections and rates have been published in 19 for convenience. Figure 4 until 4 1 until 4 show an overview of the average reaction whites dominating their respective reaction rates as shown in equation 6. The whites are directly related to the transmission coefficient 3. The Hauser Fechbar formula from equation 5, it can be inferred that the cross-section will be sensitive to the smaller transmission coefficient appearing in the neometer. The same holds for reaction rates with astrophysical transmission coefficients accounting for excited state contributions. Voids of comparable size in the numerator packed the cross-section or rate equally. Voids of comparable size may also lead to branching in a reaction path when several reaction channels compete. See, for example, the reference 45 and 46. If the total white in the denominator is dominated by a large white not appearing in the numerator, the reaction rate will also be sensitive to the variation of the white. Therefore, the rate can be sensitive to more than one white. These cases are marked as unknown in the figure 1T. To further identify the contributing whites, it will be necessary to consult the detailed tables of 19. The fact that the weight depends on the relative energy and also the span of the involved levels has the important consequence that the excited state contributions to the stellar rate may exhibit different sensitivities than the contribution from the reactions on the gases of the nucleus. This in turn implies that a comparison between data and theory for gases reactions may not provide the required information to improve the prediction of the stellar rate. This is especially relevant at the elevated temperatures of explosive nucleosynthesis with their tiny gases contribution to the stellar rate. See the online table and references for 1943 and 44. Also notes for C is the fact that the particle walls not only scale with the relative interaction energy of absorbed or emitted particles, but also are affected by the proton to neutron ratio. For example, figure 3 and 4 show that the neutron captures on a neutron reaching nuclides are mostly sensitive to the gamma white, whereas the proton rich nuclides, either the dependence On the neutron, white is dominating, or neutron and gamma white are both affecting the rate level unknown. This is because the gamma white is much smaller than the neutron white for neutron-rich nuclides, whereas the neutron white becomes comparable to or smaller than the gamma white for proton-rich nuclides. Obviously, predictions can and should be compared to data. It is crucial, however, to perform the comparison in an appropriate and informed manner, considering several important aspects as mentioned above. When comparing experimental and theoretical gases cross sections, translation of the result into an impact on an astrophysical rate may not be straightforward. When comparing rates, it is important to identify whether the rate has been derived from measured gas cross section or whether it includes the temperature dependent contributions of excited states. Perhaps less obvious, it is important to note whether the comparison involves actually calculated rates or fits of such rates. For example, in the reaction library parameterization introduced above, fits may deviate from the actually predicted rates, and disagreement between the data and fit may hint at a problem with the data fit and not necessarily with the actual prediction. On the other hand, if such fits are used in reaction networks in astrophysical simulations, it is important to identify and rectify such a problem as it may impact the results of the simulation. Evaluating the quality of fits is not straightforward either way. A large deviation is permissible for temperature regions where forward and reverse rate would be in equilibrium, and especially in environment exhibiting equilibrium between a group of rates or R rates. For these cases, the individual rates are not important and abundances are calculated from the equilibrium formula. See, for example, the reference 5. This is the case for the temperature. When the temperature is greater or equal to the 5 gigakelvin, although some equilibration may already occur above the 1 gigakelvin. Larger deviations between the calculated rate and its fit are also permissible for situations in which the rate is extremely slow and therefore will not cause an appreciable change in abundance across a time window defined by the duration of the nucleosynthesis process. In explosive environment, the relevant time scale is on the order of a few seconds plus the time to allow decades of short-lived products. This is relevant for the reactions between the charged particles for which the Coulomb barrier strongly suppresses the reaction at low temperature. The present on the tables of feed parameters also include a measure of the feed quality taking into account the criteria relevant temperature, window reaction speed described above. Due to the large number of rates, the feeds were obtained using an automated feed procedure which worked well for the majority of cases but locally gave rise to larger deviations. An overview of the deviations is shown here in figure 5 and 4. So figure 1 shows the type of the reaction which dominating the size of proton induced astrophysical reaction rates at 3 gigakelvin. Dominating white is identified by the color of the square for the target nuclide. The assignment unknown means that the rate is sensitive to more than one white of comparable size, except to capture reactions. Only reactions with positive Q value are shown. This figure was created using the rate sensitivity given in reference 19. Thank you so much for watching my tutorial video until the end. Today is the 20th of June 2026. Time is 1:38 p.m.